Well, howdy, students. As I've told you, I owe you 2 extra lectures, some content that we weren't able to cover during class because of the week we missed due to the quarantine. And today's topic is Chapter 11. We're going to be learning about systems of linear equations. I'd like to start with a bit of a story problem. Let's say you're on vacation in a foreign land, and the currency there is gold and silver coins. Now, you don't know what each of these is worth or what the exchange rate is between them. You don't know how many units of currency each one is worth. You're going to try to work it out yourself because you're third in line at the shop and you don't know what to pay with. So let's see. The first customer in line, they get up to the till and their total is 73 fantasy dollars. Let's see if I can get rid of this once and for all. See how that works. Their total is 73 fantasy dollars, and they pay 5 gold, and they overpaid a little bit, so they get 3 silver as change. So what we know is that 5 gold minus 3 silver is 73 fantasy dollars. And that's how I'm going to write that. I'll write G for the value of gold and S for the value of silver. And that way that statement right there says, well, 5 gold coins is $73 if you then get 3 silver back. So that's our first customer. Second customer, the one right in front of you. So now we're down to the line. Their total is 54 fantasy dollars. And they pay with 2 gold and 5 silver. And this appears to be exact change. So we can deduce that 2 gold plus 5 silver is exactly 54 fantasy dollars. Now you've got a handful each of gold and silver coins, and your total comes to, I don't know, let's say 23 fantasy dollars. You need to decide in a big hurry what you're going to pay with. Let's say your total is 21 fantasy dollars. You need to decide in a big hurry what you're going to hand the cashier so that you don't make a scene and embarrass yourself at the Fantasyland store. So we need to know how much is each coin worth. What's the value of G? What's the value of S? Now, the good news is we have exactly enough information to solve this problem. So I can write here, instead of G and S, I'm going to write X and Y. That's typically how we're going to write these. So instead of 2G plus 5S is 54, I'll write 2X plus 5Y is 54. And these are the same variables as the Cartesian plane for a reason. I'll explain why in a moment. Let's see, the other customer, they had 5x minus 3y equals 73. So the good news is that this is exactly enough information to solve the problem. See, we've got 2 variables here, x and y, 2 unknowns. But the good news is we've got 2 different equations. So we have as much information as we have freedom in the problem. So this should allow us to specify exactly one answer. So a solution is an ordered pair x comma y such that these values satisfy both equations. Now I'll tell you how to get the solution in a moment, but right now I want to show you what it means to be a solution. It turns out that the correct value is that a gold coin is worth 17 fantasy dollars and a silver coin is worth 4 fantasy dollars. And the reason that works is because 2 times 17 plus 5 times 4, well, that's 34 plus 20. And so that equals exactly 54. Whoops, looks like I got part of it, but not all of it. Oh, it went away. Dang. And then in the other equation, we had 5x minus 3y, so 5 times 17 minus 3 times 4. Well, 5 times 17 is 84, and 3 times 4 is... Nope, 5 times 17 is 85, not 84, my bad. And 3 times 4 is 12. 85 minus 12 really is 73. So this, this solution satisfies both equations simultaneously. That's why another word for this kind of problem, we could call it a system of equations, or we could call it simultaneous linear equations. So your solution has to work for both equations simultaneously. I mean, otherwise, another answer could be something like gold is 32 and silver is 2. And then 2 times 32 would be 64. 5 times 2 would be 10. Whoops. If there were a minus sign here, that would work. Let me rethink that. You could have gold is 27 and silver is 0, and that would solve the first equation, but not the second one. We need a solution that solves both, and for a reason I'll show you shortly, there is only one solution that's going to fit both. So how can we find this solution on our own? Well, again, simultaneous linear equations. We're going to call those 2 or more equations with 2 or more variables. So in this last case, it was 2 and 2. And we want a solution that satisfies both. Here's a simpler example to get us started with. 3y plus, oops, I need to be a little faster. 3x plus 2y equals 6, and x plus 3y equals -5. Now there is exactly one solution. In this case, xy equals 4, -3. And that's because 3 times 4 is 12. 2 times -3 is -6. 12 minus 6 is 6. 4 plus 3 times -3 is -9. Really is -5. So this solution works in both equations. How can we get this solution? I have 2 methods for you. Either of these methods will work for every problem. So if you wanted, you could just learn one of them. But I suggest you learn both because depending on the problem, one or the other method might be faster. Now these 2 methods, the first one is called substitution. The other one's called elimination. And I recommend you learn both substitution and elimination because depending on the situation you're in, there might be a shortcut in one or the other of them. And I'll show you how to recognize those soon. We can use our experience with these kinds of problems to guess which one will be faster. So in substitution, we're going to do 3 things. Solve the equation of your choice. You can pick either one for the variable of your choice. So we can pick either equation and either variable and try to solve. Now, given this array of equations, let's see, I could solve this one for x. X would be 6 minus 2y divided by 3. Or I could solve this one for y. It would be -5 minus x divided by 3. Now that fraction is making me uncomfortable, so I'm going to solve the second equation for x. Instead of having x plus 3y equals -5, I'm going to write x equals -5 minus 3y. That's a solution without any fractions. So it's completely up to us which one we pick. I would say go with the path of least resistance. Pick the one that's the easiest to solve and gives the simplest looking answer. Now this second step is where the method gets its name. We're going to substitute. We've seen this. This is the process where we, if you're trying to evaluate a function at an expression you're substituting, you're putting one expression in where another one used to be. And in this case, we're going to substitute your solution into the other equation. Now see, in this other equation, what we had was 3x plus 2y equals 6. But if I substitute this expression in, x is the same as negative 5 minus 3y. So I'm going to put that in for x right here, and let's see what we get. We get 3 times negative 5 minus 3y plus 2y equals 6. And what this has done for us is that this right here is a linear equation in one variable. The only variable is y, and this is a linear equation, so we know how to solve this. I'll distribute the 3. This is negative 15 minus 9y plus 2y equals 6. Combine like terms, add the 15. Negative 7y equals, what's 6 plus 15? 21. So I combined these, and then I added the 15 to the 6. So negative 7y equals 21, divide by negative 7, and we get y equals negative 3, which is, like I said, what the solution should be, as you can see here. Now, the third and final step is the easiest. Now that we know the value of y, we solve the other equation, the one we don't have right now, the one you picked originally. If I plug y equals negative 3 into this equation, well, now that I look at it, we can solve either equation. Since we now know the value of one of our variables, I can plug that back into either equation. How about x plus 3y equals negative 5? If I stick this y equals negative 3 in here, so I'll be replacing this y with a negative 3, then this equation says x minus 9 equals negative 5. So I add 9 and I get x equals 4. And then I'm going to write my solution, x comma y equals 4, negative 3. It's not a coincidence that this looks like a point in the Cartesian plane. The geometry of the Cartesian plane is how I'll explain why we get one solution. I'll explain that in just a bit. But for now, this is what we have. X comma y equals 4, negative 3. So we got our solution. Like I said, this method will always work. Any system of equations that can be solved, this will solve it. Oh yeah, gotcha. No, not the whole thing. Dang. I'm trying to get rid of that little pop-up box, but haven't been fast enough to catch it with ad block yet. I'll get it next time. Okay. First though, let me show you the second method. Method 2 is called elimination. Now in method 2, we're going to, step 1, multiply the equations by constants on both sides, of course, to keep the balance. How does that help us? What we're going to try to do is match coefficients and cancel. Now these English steps are intentionally vague. It'll look a lot easier when I show you how to do this in the context of an example. Here's what I could do. The key here is matching coefficients, and as usual, we have a lot of choice here. If my system again was 3x plus 2y equals 6, and x plus 3y equals negative 5, maybe I could match up the y's. See, I have two y's here, and I have three y's here, I'd like to have the same amount of y in each equation. Now I can choose, do I want to match up the y's or do I want to match up the x's? It's up to me. Here's what I'm going to do. I'm going to multiply both sides of this first equation by 3. Remember to distribute that 3 on the left side, so it's going to say 9x plus 6y equals 18. And this second equation, I'm going to multiply both sides by -2. And again, remember to distribute that on the left. That's going to say -2x minus 6y equals 10. And this minus 6y is what I wanted. Because if I put these two equations together, 9x plus 6y equals 18, and -2x minus 6y equals 10. Now, this is a step that I don't think we've used before. This is a new kind of algebra, which is to say, if the first left side equals the first right side, and the second left side equals the second right side, so 9x plus 6y really is 18, -2x minus 6y is really 10, then if I take this expression on the left and add it to this expression on the left, the two of them have to add up to 28, 18 plus 10, because this one's 18 and this one's 10. So if I take these two equations and add the left side to the left side and the right side to the right side, both sides have to be equal to 28. And down here, this is the magic of this method. This is what we get is 9x minus 2x. So 9x plus -2x is 7x. But 6y plus -6y is 0y. So all we're left with is 7x equals 28, which tells us that x equals 4. So we matched up these y's. I chose these numbers so that these two expressions would be the same. I chose these numbers so that these two expressions would be the same. So that's what I mean by matching coefficients. And this is what I mean by cancel. You add your two equations together. The new equations, the ones that have a matching coefficient. And when you add them together and cancel, well, hey, now you've got a variable by itself and you can solve for it. So now x equals 4. And final step is to finish this exactly like you would a substitution problem. I'm going to take my x equals 4 and I can pick either equation to plug it into. I know that 3x plus 2y equals 6, for example, so that means 3 times 4 plus 2y equals 6. Subtract the 12 from both sides, and 2y equals -6. Divide by 2, and we know that y equals -3. Finally, I'll write my solution. X comma y equals 4, -3. And this is the same solution we got before. So like I said, as long as your system is solvable, and as long as it's linear, so I can't have like powers or weird functions, either of these methods will work for any problem. It doesn't matter what your system is. If it's solvable, both of these methods work. So they're interchangeable. It's just up to you which one to use, because on some problems, substitution is faster, and on some problems, elimination is faster. So I'm going to break that off and call that the intro.